Hello everybody and welcome to presentation 7. In this screencast I'm going to talk about integer multiplication and division. As I often do, I'd like to start by establishing some context in terms of things that we're already familiar with. So since we're going to talk multiplication and division, let's do a quick review of how multiplication works in the first place, or how we often do it with pen and paper. So let's just multiply the value is 128 by 17. Now, I'm going to go through the steps that you've all used 1,000, 1,000,000, who knows how many times before in the past, but I'm going to do something a little different. I'm going to actually do them a little bit out of order relative to what you're probably used to, just to demonstrate that it works just fine to do so, which we should know, but it might not occur to us, and B, to help us to recognize what's actually happening. So sometimes by shifting up a routine, we look closer at it and it deepens our understanding. So I'm beginning by establishing some columns and marking the tens value, the power of tens associated with each of these positions. Again, remember we're using place value, and so we're coding values by position. All right, so we then see that we actually have 1 times 10 to the second plus 2 times 10 to the first plus 8 times 10 to the 0 being multiplied by 1 times 10 to the first plus 7 times 10 to the 0. Okay? All right, so to begin with, I'm actually going to start by multiplying with the 10 in the 17. Right? So 10 times 128. Well, that's going to be 1,280. Right? Why is that? Well, when we're going through as kids and we're taught to do multiplication, we would have just gone, oh, well, I shift when I do the tens. I would have ended up having shifted to the left because it was the second number that I was multiplying, and then I would have multiplied digit by digit and gotten the value. Look what's happened here. Okay, by doing this a little out of order, I'm hoping that you'll see why you had shifted to the left. It wasn't just because it was the second value you were multiplying. It's because you are now working in the tens position, or the 10 to the first powers position, right? So it wasn't 1 times 128, it was 10 times 128, okay? So hopefully that's kind of standing out to you. Now I'll multiply the 7 by the 128, but I'm going to do it still a little bit differently than you're probably accustomed to. So 7 times 8 is 56. Okay, so I'm just writing that the 5 in the tens place and the 6 in the ones place. Often we do this thing where we would have just written the 6 and brought the 5 up into the tens column and just written it up there. And you've probably done that so many times that you didn't even think about what it meant. Well, what did it mean? Well, what it meant was I had 56, which meant there were 5 extra tens. Right? I can't put 5 tens in the units position, so we would just put them up there to use them later. Well, the notation's a little bit screwy if you think about it, because you could easily get disoriented and end up multiplying the 7 by the 5 that you wrote up there instead of multiplying the 7 by the 2. In fact, you probably made that mistake and gotten the wrong answer from time to time. Okay, so I'm just actually going to go ahead and write the 56 here, right? No harm in that. I'm going to add it to the 1280 and everything else when I'm done. So it doesn't really matter where I put it, so I'll just put it there. All right, then I've multiplied the 7 by the 2. Or more accurately, that's 7 times 20, which is 140. Okay, and then finally 7 times 100. So the 7 goes down there. Now, again, the way that we were taught to do this, kind of by rote without thinking about it, we would have worked our way all the way down to the 7 and just been carrying things over and probably not even fully realized we were actually multiplying 7 by 100. We just say, oh, this is 7 times 1. Okay, so I just wanted to draw this out. I hope you don't think that was too silly of an exercise. And then here it is, if we do it the way that most of us were taught, we just fire off, oh, there's the 7 times the 128. Okay, and then we write down a 0 to force us to shift to the left, and there's the 1 times 128, and then we add all that together. Same answer, but perhaps a little more meaningful now, having gone through it in a slightly different order. Okay, now a couple things I want to point out. Look at the first value that we're multiplying, 128. It has 3 digits. Okay, so I'm going to say n is the first number, and it has 3 digits. 3 decimal digits. The second digit, the second value, we'll call it m. It has 2 digits. The product, we'll just call it p. It has 4 digits. Okay, so just like with addition, we've seen that our result, when we do multiplication, can end up having more digits in it than the two values we're multiplying together. How bad can this be? Well, let's take a look. 9 is the largest single digit value we can have in base 10. So 9 times 9 is 81. And we see then that we had one digit times one digit and got 2 digits. Okay, so it looks like we doubled the number of digits that we had there. Or that's maybe not the best way to say it. we've summed, actually. We'll say we've summed the digits that are there. That'll end up being more accurate. Okay, let's extend this though. Let's say we have the largest 2-digit values that we can multiply together, 99 times 99. If we work through the processes we've been taught, we end up with 9,801. And so that's two 2-digit values gave us a 4-digit value. So again, we seem to have added up the digits in the two values that are being multiplied together as a predictor of the number of digits we'd need in our final product. Okay, let's jump into binary multiplication now that we're all warmed up. So here's a binary number, a couple of binary numbers. All right, so 1011 times 0100. All right, so let's see, that's going to be 8 plus 3, so 11 times 4. Okay, so we go ahead and work through the multiplication the same way that we would have done decimal multiplication. So we'll grab a bit, in this case, and we'll multiply it by the other value, and then move on to the next bit, multiply it by the other value, and so forth, and sum these things together. Now, it turns out that in binary, multiplication acts very much like the AND operation. Okay, so 0 times 1 is going to be 0, right? And that's going to happen all the way across, and that's kind of like AND. 0 ANDed with anything is going to give us 0. Okay, we move on then to the next bit, and that's now in the 2 to the first powers position, so we'll write our product accordingly so that we can keep our columns all lined up. All of our powers of 2 are in the same column. Okay, so now it gets interesting because now we're going to multiply this 1, which is in the 2 to the second position, by the entire value. And so we'll step through that, and we'll see that 1 times 1 is 1. 1 times 1 is 1 again, 1 times 0 is 0, and 1 times 1 is 1. So again, here's where we see the other half of the AND. 1 ANDed with anything is the thing. Okay, so binary multiplication becomes very easy. If you see a 0, just put zeros. If you see a 1, put the number. Okay, and then just make sure that you got your columns lined up. Okay, repeat for the last digit, sum these things together, and we have our result. Okay, now, if we look at the number of bits that we used in this case, we see on the first, in the case of the first number, we had 4. The second number appears to have had 4. And then our final value has 6. When you look at the second number, you might argue that, well, you only really needed 3 bits for that value, right? So it depends how you want to interpret this. We're going to go ahead and say that, yes, this is a 4-digit value, excuse me, a 4-bit value, but that not all 4-bit values are created equal, right? So this one, the most significant bit was in the 2 to the second powers position. And we see that we didn't end up with 8 bits, which we might have anticipated. We only ended up with 6. Okay, but that's not really a worst case scenario, is it? Let's see what could happen. Okay, and try to inform the intuition for the conclusion the book gives us. So to cut to the chase, the book tells us if I have an n-bit number and I'm multiplying it by an m-bit number, then the possible number of bits I may need is n plus m. Or said another way, the book likes to use w for the word width. So if I'm multiplying two values that are w bits wide, then I may need up to 2 times w bits wide positions to hold the product. Or in other words, you have doubled then the word width. Why? Well, because you had w bits and you multiplied by w bits, and we saw that there's this pattern kind of emerging. But I want to inform the intuition for that. So here's how we're going to do it. Again, I'm working with 4-bit values. I'm pretending I have a 4-bit machine. If you have a larger machine, the same idea would apply. It's just that where I say 4, you'd want to apply 16, 32, 64 bits, whatever, okay? So in this case, we're going to pretend we're multiplying 4-bit values on this computer, on some computer, some very limited computer, okay? Now, here I've got the largest unsigned value that I can have, which would in this case be 15. The largest unsigned word, the largest unsigned value that would fit in a word if my machine's a 4-bit machine. Okay, so what I want to point out is, let's just assume that there's a 1 in the most significant bit of the other word that I'm multiplying by, okay? So what happens there? Well, we already saw that we are basically ANDing across those bits, and we're going to end up writing all these 4. Now notice the position that those bits are in. Okay, because I'm multiplying by the bit that is in the 2 to the 3rd power position, the smallest, the least significant bit, I shouldn't say the smallest, how should I say this? There are a bunch of zeros, of course, right here. Okay, but the fact is that anything that I multiply this bit by is at the very least then going to produce a bit that is in the 2 to the 3rd power's position, right? Effectively, I am shifting the original value, right, 1, 1, 1, 1, to the left so that it lines up with the bit position of the bit I'm multiplying by, right? Okay, so what does that do? Well, that's going to shift 3 bits off to the left further than they were before, right? Hopefully you can see that. So right out of the gate, if I have two 4-bit values and I'm multiplying them, and both of them have 1s, for instance, in the most significant bit, then that 1 in the second operand's most significant bit is going to shift everything from the other value, the other number. It's going to shift all those bits to the left. So right out of the gate, you're going to have 3 bits. 3-bit positions. You're going to need 3-bit positions that you didn't have before, right? In the product. I hope this is making sense. Okay, so so I've picked up 3 bits. So I have 2 4-bit numbers. Now I know I'm going to need at least 7 bits in the product. Well, we're not done, right? We've got these question marks here. What could happen with these other bits? Well, let's just pretend for a second that the least significant bit has a 1 in it. Well, that would mean that I would end up adding the product of the 1 with the 1 in the second value with all of the bits in the first value. And whatever the other bits in the middle produced, at some point I'm going to add these 2 values that I've already written out. Okay, I'm going to add this stuff to this stuff. There may be other stuff here. There's going to be, depending, and I don't know what it is, but I'm at least going to add those 2 sets of values. So when I do that, I'm adding 1s to 0s for the first 3 bits. Then these 2 down the center here, those are going to give me a value of 2, at least. Okay, so there's going to be a 2, which is going to put a 0, and again, it could be greater than a 2 there, but at the very least, I'm going to have a 0 with a carry of at least a 1 here, right? So I put the 1 up there, which is then going to cause a rollover effect, and voila, I've got this carry sitting over here now, right, in the n plus 4th position if n was the number of bits I started with. Okay, so here we see that indeed, I wanted to point out here also that these 2 bits in the middle, it turns out they're not going to be able to push values any further. They're not going to be able to cause us to consume any more bits than we already have, and I'll leave that to you to confirm that. But the point is that we had 2 4-bit values, we multiplied them, and we ended up with an 8-bit value. I really wanted to demo this to kind of hammer the point home. What's causing this to happen? Well, that first bit is predominantly responsible for what's happening here, because it effectively shifts that first value all the way over in our very first step. Okay, and then from there it's uphill. Anything else is going to cause us to pop over into that n plus 4th position. Okay, so just kind of a summary then of multiplication. The goal when we're doing multiplication of the computer is to compute a product W-bit numbers. So if we have a 32-bit machine, 32-bit numbers x and y, these could be signed or unsigned. We want this to work in both cases. But as we've seen, the result can be bigger than W bits. In fact, it could be up to 2 W bits. All right. If we're doing signed multiplication, we didn't mess with it there, but the ideas are the same. If we do 2's complement, multiplication of 2's complement numbers, the minimum number that we could get, in other words, the largest magnitude negative value that we could get, could take up to 2 times W minus 1 bits. The largest positive product we could end up with, this is kind of interesting to think about, the largest positive product we could end up with is not going to come from multiplying together 2 positive values, because if you recall, the largest magnitude of a value that we can have in unsigned 2's complement numbers is actually going to be a negative number, right? So if I have a 4-bit machine, then the largest negative number that I can write is -8. The largest positive number that I can write is only a +7. And it works the same way no matter how large the word is. Okay, so why do I care about that in this case? Well, because -8 times -8 is 64, right? And 7 times 7 is only 49. Because we're multiplying 2 negative numbers, we get a positive result. So in order to have actually the largest positive number that we can get, ironically, that's going to happen by squaring T min, or 2's complement min. Perhaps that already stood out to you, and you're yawning right now, but my guess is that for many of us that looked a little funny when we first saw that, so I just wanted to explain why and what's happening there. All right, so again, we end up needing more bits than we have in our word size. So if we wanted to get the exact result, we need to have this ever-growing word size, which we can't do in the hardware. So we end up just truncating, right? And we only keep W bits, which effectively means, again, we're doing modular arithmetic. We've computed, you could pretend we computed the result and then divided by 2 to the W, which caused all that other stuff to turn into zeros, and we just keep the W bits that we started with, okay, the word width we started with. If we do need to compute products that take more bits than our word width, this can be done in software, and indeed is done in software, using arithmetic packages that manage this overflow problem by using multiple variables and so on and so forth. Okay, multiple memory locations. All right, so here's just another visual of what's going on here. So if I'm multiplying U and V, and they are W bits wide, then the actual product could be up to 2 times W bits wide, and we'll just discard the upper W bits. Okay, so no problem there. And as I said, this is effectively implementing modular arithmetic. Okay, when we do signed multiplication, same kind of thing happens. We ignore the high order bits. Now, if you actually go through the work to write down these bits, you'll see that they don't look exactly the same as if we were doing the unsigned operations. But it turns out that the lower bits are the same. And there's a proof in the book. I'm not going to walk through it at this time. But there is, or at the very least, an explanation in the book that walks through, hey, look, here are these summations, and a bunch of things cancel out, and so you're actually able to show that the part of the number that you keep ends up being identical to the part, to the value that you'd have gotten if you'd done the unsigned multiplication. And so in other words, it works. Okay, so it looks a little funny, but it ends up that it works, and it's not just a fluke, it's always going to work. Okay. All right. This being said, I've used the word shifting in this conversation. We're talking about multiplication, about shifting things to the left, and so on and so forth. And as has been pointed out in class, if we're multiplying by a power of 2, it has the effect of shifting the number that we're operating on to the left by the power of that power, by the k in that 2 to the k, that power of 2, okay? So if k is the power, then we're going to shift the bits to the left by k. This diagram down here looks a little bit funny. There's a k right here, and they're trying to indicate that that is the kth position, okay, or the kth power of 2 in this number right here. Okay, so hopefully that's making a little bit of sense. And the result is, boom, it shifts all of this stuff this way. And hopefully you saw that happen when I was actually writing out the multiplication, that we would have been taking these bits and writing them down here. And you see that it forces everything into this column. So that's why that's happening. You could just imagine a bunch of zeros with a single one sitting in that position that's going to cause the shift to happen. Okay? And then what happens if the result of shifting pushes important bits too far to the left so that they're hanging out outside of our word? Well, they'll just be cut off and truncated. Okay? Just as if we were doing, here we're kind of showing, look, this is what happens if you did multiplication. The point we're trying to make here on this slide is that if you just did the left shift, well, there'd be this truncation, and that's exactly what would have happened if you'd actually done the work to go through the multiplication in the first place, so nothing's lost. Turns out that it works the same on signed values as it does on unsigned values, and that's going to work until there's overflow. But if there's overflow, there would have been overflow when we did multiplication anyway, and so it works out the same. We can safely do these shifts. Okay, they give some examples then. So shifting to the left by 3 bits is the same as multiplying by 8. And then they show us something cool. All right, they talk to us in the book about how if we're multiplying by constants, the computer might actually, the compiler might actually be able to actually speed up our code by doing a kind of a cool optimization. So the basic idea is, here's u being multiplied by a constant. 2 to the 5th is not 24, of course, but it's close. It's relatively close, okay? So in fact, it's 32. If I subtract 2 to the 3rd from it, then I am subtracting 8, and so I get 24. Okay, so I could write the value 24 as 32 minus 8. All right, u is the number I want to multiply by 24. And so since 24 is equal to 32 minus 8, then I could write u times 24 as u times 32. And u times 32 is the same as u left shifted by 5 bits. I then would need to subtract. Okay, so we're just distributing here. You see the u times 32, and now there needs to be a minus u times 8. That is the same as u left shifted by 3 bits subtracted from that original product. Okay, so we can figure that out pretty quickly. The compiler can figure that out and create then these 2 shifts plus a subtract. So why would we care? Well, because doing 2 shifts and a subtract probably only takes me 3 clock cycles. Whereas the multiply may take a dozen or dozens. It takes longer is the point. And so the compiler is going to look for opportunities to do that. It'll do it for you behind the scenes. You don't have to worry about it. But it is important to understand that this can be done. And if you are being forced to hand jam something at any point, then you might want to keep this in mind as a way that you could speed up your operations. What about dividing? Okay, so we can also use shifting to do division. Shifting to the right ends up being the same as by number of k bits ends up being the same as dividing by 2 to the kth, 2 to the kth power. Okay, now we're going to use, when we're working with unsigned values, we're going to use a logical shift, and hopefully you caught from the reading that means that we're not going to sign extend. So in other words, as we move the bits to the right, we're just going to pad with zeros on the front. Okay. Oh, there's some notation here I wanted to emphasize. So where you see these kind of brackets that have the square brackets missing their tops. Okay, this is known as the floor function, and it basically means that we're always going to round down. Why is that significant? Well, as you shift bits to the right, somewhere there's a point there, right? So in the decimal system, it's a decimal point. In the binary system, we could say that it's a binary point, right? Where everything to the left of it is a positive power of 2, and everything to the right is a negative power of 2. In other words, those are fractional bits. Well, we don't keep those when we're doing integer stuff, and so you can say that if we don't have a whole number, there's a fraction, well, we just threw away the fractional part, and so that's equivalent to always rounding down, okay, rounding down to the next integer. In other words, we're moving towards 0. So if we have a fractional value, we're just going to whack it off and move towards 0, okay? And that's being demonstrated right there. Okay, so what happened? Well, when we divided by 2 to the k, we shifted everything to the right. We could equivalently have shifted by k bits to the right, and you see that that portion of the original value u has been moved to the right side of the binary point and will be discarded in the result. Okay, here are some examples. Feel free to pause the video and walk through them. I will also have these slides posted up on Learning Suite, so you can peruse them at your leisure and study this chart more closely. For now, I'm going to move on. Okay, so what about sign division via right shifting? So we talked about unsigned and saw that that works pretty good. But what about signed? Well, the book hums and haws and points out that with signed division, things act a little bit differently, and I'm going to demonstrate that weird behavior. I'm going to go ahead and put out there right now that because there's kind of this inconsistent behavior between signed and unsigned division by shifting, from what I can tell with a little bit of reading I did, there's actually not an established standard in C relative to how this should be handled. So the book suggests a way of dealing with the issue. My understanding is that you actually can't count on everyone and their compilers having, well, not just the compiler. Yeah, basically you can't count on everybody handling the problem this way. And so in C, for instance, trying to accomplish division by right shifting and whatnot and how that should be handled is just basically implementation specific. So it's up to you what you do, kind of thing. Let's just look at this demo. Okay, so -1. On a 4-bit machine, -1 is all ones. On a 32-bit machine, -1 is all ones. What I'm about to show you here would be consistent no matter what the word size of the machine was. Let's go ahead and right shift this value by 1 bit. That would be the same as dividing by, well, in this case I'm dividing by 1. That's not going to be very useful, is it? I just realized my demo's not real great, but you know what? We can actually make the same point just by pretending that I actually wrote a 0 there, okay? And so now there's another 1 over here. So we're dividing it by, what am I talking about? I was fine. Okay, so we're going to right shift by 1 bit, which is equivalent to dividing by 2. It's late. I'm staring at 1s and seeing 1s instead of 2s. Some of you will get that, some of you won't. So right shifting by 1 bit, that is, in this case, dividing by a 2. So the value shifts to the right, and we see that the rightmost bit gets whacked off. All right. However, we're sign extending. We're not doing a logical shift. We're doing an arithmetic shift because we're dealing with signed values. We want a negative number to stay negative when we divide it by a positive number. Here we're dividing it by a 2. So we need to sign extend. So we use the arithmetic shift. So the 1 gets put back. Well, this value is still -1. What? We're saying that -1 divided by 2 is equal to -1? Yes, that's what we're saying in this case. Because in this case, the behavior is not consistent with unsigned division. With unsigned and positive division, when we divide by shifting, we round down towards 0. Right? We're using kind of this floor function, and we're moving towards 0. When we do negative division by the shift, we still move down. Okay, so -1 divided by 2 should be a -0.5, right? Well, we might expect then that some kind of truncation would mean that it rounds towards 0 and we would get a 0. But because of the way that we're sign extending, that's not what happens. We actually have we're still moving in the same direction, so our negative 0.5 gets rounded down to a negative 1. So I can never actually get to 0 the way that I can when I'm dividing unsigned or positive values by shifting them to the right. Okay, so hopefully that makes some sense, and you're seeing kind of the problem we have, that the rounding behavior relative to 0 is different. For unsigned values, we're heading towards 0. For signed negative values, we're heading away from 0. Again, the book provides an approach that we can use to bias our numbers before we do this division by shifting, and so in the end, it does move towards 0 as well. But again, that particular implementation of division by shifting is apparently not standardized, and not everyone will handle it that way. And so you're not actually required to implement it that way. Okay, that's all I have for you. That's kind of a drink from a fire hose. Remember, you can go back and review this, play at double speed, whatever you need to do. But hopefully it's given you a bit more foundation that you can use to understand both what the book's talking about as well as the things that we will be doing going forth the rest of the semester when we're dealing with bits and multiplication and so forth. All right, thanks. Until next time.